maybe I can start. So yeah, so then now somehow I have to try to explain the refinements of Yamanoi's what Yamano did to actually prove this pseudo hyperbolicity. So it will get technical at some point. So I will start just by talking about tautness, which is, I mean, I guess interesting also, because maybe it's not so much used. So I guess it's interesting to say something about this. And just recall what Erwan already told us. So if you take X complex variety, complex manifold, and you take a delta in X, X a closed subset. So for this definition, I guess you could take anything, but in practice it will be a Zariski closed subset. Then you say that X is Kobayashi hyperbolic modulo delta if the distance for any P and Q in X, if the distance with respect to the Kobayashi metric in P and Q is equal to 0, then this would imply that actually P and Q both belong to delta. And we said that X is taut modulo delta if for any sequence of maps in delta to X, then either one, there exists a converging subsequence. Yeah. From sorry, from D to X. Thank you. Or two, for any K in a D compact, and for any L in the complement of delta compact, there exists N0 in N such that F of Fn of K intersected with L is equal to empty for all N bigger than N0. Okay, so this basically means that if you take say your variety X like this, if you have your delta like this, you should typically think of X being compact and L being the complement of some open subset containing delta. So this would be somehow L. And so this basically tells you, or L, yes, something like this. And this tells you that either you have a converging subsequence, or the image of your disk, so Fn of B should be arbitrarily close to delta. That's the idea. And what Erwan already mentioned is that why is this interesting here? It's a theorem of Hirnan and maybe Kobayashi. Presumably, you can add Kobayashi to most of the theorems. Kobayashi hyperbolicity is the classical thing. You would have that if X is taut modulo delta, then X is Kobayashi hyperbolic modulo delta. And I will actually prove this, right? So just because it's not so hard, and so I maybe it's the idea of proof, so which I took from Kobayashi's book. So the idea of proof is as follows. It's that say you have your delta here, which is your bad locus, and you suppose by contradiction so you suppose this is not true, that there exists a p in the complement of delta, and that there exists q in x, such that the distance in q in x from p to q is actually equal to 0. So philosophically, I mean, you can suppose that q is actually on delta, just to make the picture more clear. It doesn't have to. And P is somewhere outside. Let me put it like this. P. Okay. And then what you do, you actually construct some open subsets around P. You can, for instance, take some polydisks, open neighborhood around P, which does not intersect delta. And inside of this polydisk, you take a slightly smaller, say, polydisk neighborhood polyt V. And the point is that you can actually show from, and I will explain how to do this a bit, from the fact that the distance between P and Q is equal to 0, that claim there exists a sequence Fn in N, included from P to X, such that Fn of the disk of radius 1 over n is not included in U for all n bigger than 1. So you can actually construct somehow a sequence of disks which somehow explode somehow outside of U. And so this is basically it's playing with some chains of disks. I will somehow explain it in a minute. And just this, of course, contradicts tautness. The claim. Contradicts tautness. So of course, if you have this, then Fn could not have a converging subsequence. So this implies Fn has no converging subsequence. And it also implies, it also contradicts 2. If you take K to be 0 inside a D, and L to be the closure of V bar. It's V bar, it's closure of V, so it's a Euclidean topology. And then, of course, F of K, which is also, sorry, and I forgot about this, Fn of 0 belongs to V for all n. Otherwise, yeah, otherwise it would have been very easy to prove this claim, but this is a condition you have to add. And yes. And so this basically, as a claim, then proves the theorem. And to prove the claim, so idea to prove the claim. So because you suppose that the distance between P and Q is equal to 0, there exists, since the distance in X between P and Q is equal to 0, there exists chain of disks. Let me write it gamma, whose length length of gamma. So from P to Q is as small as we want. Okay. And if the claim is false, so if the claim is false, then this implies that there exists some delta bigger than 0, such that in fact f of p, the disk of radius delta, is included in U for all f from d to x, such that f of 0 belongs to v by contradiction again. But this will not be possible because the idea is, so let me just write a picture. So suppose that you have such a delta, and then what you do, you say, okay, you have your chain of disk as small as you want. So you start from P, then you go to some other point, P1 here, P2, and you P3, and at some point you go out of your V, and then you go to Q, and so if I denote PK, the first guy, the first point in your chain of disk, such that you are outside of V. So this means that all the chains before this point here are actually inside of V. Then you can actually apply this hypothesis to say that for all the first disks, you know that the image of the very small disk inside of this given disk you have, so maybe means the disk themselves, they could go outside of you, right? But at least the image of a very small disk is inside of you. But the point is that because you can choose your length as small as you want, then you can say that actually the points which are relevant here are actually lying already in this very small disk. Just because yeah, you can suppose, for instance, that the length here is smaller than delta, and or delta over 2 or whatever. And so the conclusion just is, let me write the conclusion. So this would imply, maybe you just have to play a bit with a thing, is that L of gamma will be bigger, well, so then some constant, which depends on somehow the relative, if you compare the distance between the Poincare metric on the small disk and the Poincare metric on the disk on the large disk, which you can do. And this will be smaller than some constant times the first length of the chains which go until here. So distance U of PG to PG plus 1, like this. And the point is that under this hypothesis, then you can actually compare this. Yes, the fact that the point is that I can actually use the distance on U here and not the distance on X. And this comes from this hypothesis here. And so this is just bigger than the distance from P to K, which is itself bigger than the distance from U to P to the complement of V, right? So to the boundary here, and which is itself bigger than 0, and alpha bigger than 0, whereas the constant here is independent on the chain of disk you choose, because basically it's just this value here. So this is how you get the contradiction. So the idea is just that you have a chain of disk, and each disk has somehow to explode inside here to make the chain go to 0. Okay. And so what? So that's the first thing I wanted to mention. And the second thing is that Yamanoi gave some criterion to an alternative criterion to tautness. So I'm not quite sure it's I don't know exactly how well known it is or not. So it's actually the argument is the following. So I attribute it to Yamanoy. Maybe it's I don't know. And so you take X compact. And you take delta in X closed. Then, well, X is taut modulo delta if and only if for any metric h on X and for any u inside of X open such that delta is included in u, and for any 0 between S between 0 and 1, there exists some constant C such that for any f from D to X with f of ds not included in U, one has that the metric with respect to H, the distance of the derivative at 0 of f with respect to H is smaller than C. So this is exactly somehow it's related, of course, to what Erwan did and bounded the Kobayashi distance. And yes, and so yeah, so okay. And just why is this interesting? So why is this interesting? And how we will actually use it, this criterion. It's because, let me just take notes. It's because if X is included in A and you have omega A as the invariant positive 114, so you just take I over 2 dz1 wedge dz1 bar plus dzn wedge dzn bar, right? Take this this metric here. Then this metric has this subharmonicity property, which was really key. And then the point is that for any f from D to X, well, in fact, if you don't even, you can, yeah, D to X. So so you can actually have X for f from D to A. You will actually have that one has that, and for any S between 0 and 1, and for any R between S and 1, you will have that the derivative, the square of the derivative of at 0 with respect to this metric here is smaller than 1 over P S squared R minus S times the integral between S and R of the integral of dt of f star omega A dt, right? And so this this somehow, it's really something which I don't, it's quite miraculous or maybe very specific to abelian varieties, is that by some harmonicity property of this function here, you actually can bound it by some characteristic function with some constants here, which are eventually won't be relevant, right? Because all those numbers will be fixed, and so this will actually provide you the constant you want. So this shows you that this lemma somehow is able to relate tautness to a value distribution theory. And yeah, so maybe I can give a hint of the proof again. And so Yamanoi doesn't state it like this. He just says that well, if you satisfy this for subvarieties of abelian varieties, then you actually tote modulo delta. But in this statement, I don't think it's ever relevant that you are in a subvariety of an abelian variety, and I guess. And right. So the easy part is this one. So this is, yes, it's not even mentioned in Yamanoi's paper, but so you suppose, just keep tautness here for the moment, and then I will erase this board again. So suppose X is taut modulo delta. Then, and suppose that this is not true by contradiction, and that the conclusion doesn't hold. Okay. Then, what it tells you that there exists, and there exists H metric on X. There exists U open such that delta is included in U, and there exists 0 between S and 1, such that for any n bigger than 0, there exists Fn from dx with such that Fn, yes, is not included in U, but the bound here explodes. It's bigger than n. Okay. So then, of course, this Fn, because of this, Fn has no converging subsequence. Simply because this goes to infinity, right? And you also, for k, you take just the closure of ds, right? So it's compact, because yeah, it's a compact set, of course. And you take L to be the complement of U, which is compact because X is supposed to be compact here, right? And then, of course, you will have that Fn of this compact set intersects the complement of U. You have Fn, okay, intersect there. It's non-empty for all n, which contradicts the second statement here in tautness. Okay, so this was very easy. So maybe slightly more difficult, not so much more difficult either, which is just some application of Arzel-Ascoli theorem, actually, is that you can prove the other direction. And so let me do this. And so suppose, let me call this, yes, okay, so suppose that all this holds, the condition holds. And you want to prove that that this holds. Okay, so you take that Fn a sequence of this yeah, in X. You also let K compact and L including X in the complement of U compact. And so you will just take, sorry, there is no delta compact. And then you will just set U to be the complement of L, right? Which will be an open subset containing delta. And so what you want to prove is that either this one has a converging subsequence or that this, for all compact, this has f of k has to land in fn of k has to land in U. So we will actually suppose that this is not true, that fn of k does not land in U for all n. I'll suppose that fn of k is not including U for all n large enough. So if up to extracting a subsequence of this, you can actually suppose that it's actually for all, you have this for all n. You can suppose. Fn of k is not included in U for all n bigger than 0, actually. And what we want to prove is that from this condition, you can actually extract the subsequence here. So what we do is, what we always do in hyperbolicity is to use Arzelà-Ascoli's theorem. And so we want to prove that Fn is equicontinuous for any sigma between 0 and 1. Fn restricted, this family here, is equicontinuous. So with respect to the metric induced, of course, by the Kobayashi distance here, and the metric induced by H here. And if you can prove that this is the case, then by Arzelà-Ascoli, implies there is this convergent subsequence. Right? And so you just have to prove this. And to prove equicontinuity, it suffices to prove bound f prime of c with respect to h uniformly on n, and in n, and z in disk of radius sigma. And so the point is that basically your hypothesis will just a priori just tell you something about f prime of 0. Hypothesis only tells you something about f prime of 0, right? But then you just have to reparameterize. So reparameterize for any in a d sigma. One has to reparameterize right? By considering 2 sigma, which goes from E sigma to from D to D, which sends 0 to Z. And then basically you just have to well, maybe I won't write all the details, but basically, if you just, you can prove that even with this reparameterization, up to taking a maybe slightly bigger disk, then you can ensure that after reparameterization here, you still have this hypothesis here, right? And so you can actually apply. So I would write to enlarging T sigma slightly. One can suppose that to say S with S bigger than 0, but can suppose that Fn composes QZ of ds is actually not included in U for all Z in D sigma. Okay, so there is a little argument to say here. It's not very difficult, just some reparameterization thing. And therefore, this will imply basically that Fn composes QZ at 0 prime with respect to H smaller than T, but this is equal to this will imply, just if you use the chain rule, that Fn of Z prime is smaller than 1 or sigma squared. So here you just have to use the chain rule and the Schwarz lemma, which tells you that at Z here, so here at Z is actually smaller than 1. Okay, you just use this and then you bound it uniformly for all sigma. Okay, and then this concludes. Okay, so this was yes, a nice part of my talk, and now we actually have to go as Erwan already mentioned. Well, to prove, to bound, the point is now to bound this sort of thing. And what Erwan used yesterday was to use a tautological inequality in some higher order jet space. And this works very well. But as soon if you don't have any, the text doesn't contain any abelian subvariety, but as soon as you have some abelian subvariety, so basically then I will recall this jet projection will not be finite. And so at points where its differential is, so points where differential is non-injective will give you some problems. Okay, so maybe just, again, let me recall just some things, what Erwan already talked about. So, if you have if X is say a compact complex, any manifold, complex manifold, then you have the so-called domain simple jet tower. So there is really in all those things about abelian subvarieties and abelian variety, one of the key points is this so-called jet projection method. That's the fact that the jet space to the abelian variety is trivial, and so you can project it onto, say, any fiber. And this map is the key to everything, pretty much, in this situation. And then you can compactify your jet space in different ways, which is somehow relevant because, or not, well, it depends. So if you can work without compactifications, this is, for instance, what Noguchi did, and other people, you can already prove many things without compactifying, but you can also compactify in different ways, and different compactification have different properties. And so in whether this is the only compactification that makes this argument work, I don't know, but this has a very nice feature, actually, which makes it work, which is somehow I will explain this here. So again, so what I just want to say is that I don't know if this is philosophically, there is no reason why you should consider this compactification here, to my understanding anyways, but maybe for technical reasons, this is essential here. Okay, and anyways, what the point is that you have, say, a chain of a tower of jet spaces, and if X is an abelian variety, what you actually have, and so, yeah, sorry, I wanted to say on each stage you have some vector bundle here, which is, and here's the key point is that if you take any lift from, say, a map from a disk to X, it will lift to, at any stage. And the point is that f prime of k will be included in a vk, belongs to vk for all v. And the point is that here you have a rank dimension of X vector bundle here, which is much smaller than the entire tangent space to xk. And so this is maybe why it's crucial here to study this. And the point in abelian varieties, so there exists this variety R and K, so N means the dimension of A, such that AK is equal to A times R and K for all K. And then you project onto R and K. But, so that's very nice, but it's not sufficient in Yamano's proof, unfortunately. For some reason, again, I don't know if this complication is purely technical. It's something I'm not, I think it would be very interesting to have a proof of this theorem, which is much simpler and maybe only relies on this thing here. But in Yamano's proof, here it is crucial to understand the jet spaces Mk for M, which is a product of an abelian variety times anything else. Right? A is abelian, and S is anything, any large variety, a smooth projective variety. And so this is actually, this comes from an induction process in order to prove the relevant inequalities on characteristic functions, which basically goes as follows. You will start with an abelian variety, and then you will cook up some abelian subvariety, and then using Poincaré's reducibility lemma, you will say, okay, up to isogeny, the abelian variety I started with is actually a product of two abelian varieties, and then one of the abelian variety will be the one on the left, and one will be the one on the right. And then maybe you have to blow up the abelian variety on the right to actually, for some technical reasons. And so this is why in this proof, products naturally appear. RNK, yeah, it's just as a central fiber. RNK is just, yeah. And so let me start with, so any, abelian variety, that's smooth projected. Okay, so that's the setting over here. And you consider so the product, which is A times S. And then I will E of A plus the tangent space at 0 of A. And the point is that the tangent space of A is, of course, just this guy, the trivial vector bundle with this as a fiber. And then you consider M. So it has a projection to the second factor. It also has a projection to the first factor. Let me write it like this. And then the point is that Tm, the tangent bundle of M, well, this is just the tangent bundle of Ta plus the tangent bundle of S, right? And so what this tells you, and because this guy is trivial, this just tells you that this guy is actually, well, let me write it like this. So A plus 2 star S. So here it's a vector bundle, trivial vector bundle with this as a fiber. And so this you can actually say, well, it's the same thing as Q star of BA, plus tangent of S, right? And so what this tells you is that basically, well, you want actually to consider this a projectivization of this space here. So let S1 to be as a projectivization of this vector bundle here. So I just recalled, yeah, I will recall it anyway. And then this is, so this is not the first stage of the domain tower, because in the first stage of the domain tower, you don't have this factor here. But what it tells you is that the first stage of the domain tower will be equal, well, to the projectivization of T of M. And so this is the projectivization of Q star V of A plus Ts. And so it will just be the fiber product of M times S, S1. But M is equal to A times S. And so this is just equal to A times S1. Okay. And moreover, you see that somehow the tangent space of M you can recover it directly from what happens on S. And so generally, so this is the first step of the construction actually. So more generally, so for any k bigger than 0, there exists a smooth projective variety. Okay. Endowed with vector bundle VK dagger such that MK is actually equal to A times SK. So just as what we had here. So here, this will just be the simple case where S is a point, right? So this is what happens here. And so this comes with a map QK SK, which is a projection on the second factor, and you will actually have VK is equal to VK star VK down. So you can actually completely reconstruct MK from this data on the fiber or on the above S. And so to prove this, so you can construct SK inductively. So of course, we just say that. So here I somehow constructed S1. I didn't even construct V1 here, but I constructed at least S1. So suppose that you have SK minus 1, which is constructed. Then you will set SK with just a projectilization of this vector space here, VK minus 1 dagger. And you will set VK dagger, which will be a subbundle of VA plus the tangent space of K by, I can actually write it here, I think, by VK XV dagger, which is a set of all psi in this guy here. So A plus TSK such that on the first factor, so of course you will project down from SK to SK minus 1 using the differential, and here we just take the identity on the left hand on the Lie A part. A star psi belongs to V, and so you have PK, which goes to this is the maximum. So and so then this construction satisfies for some tautological reason that you can actually recover VK. Okay. And yeah, so now in the last few minutes, I will just tell you what sort of thing we are actually looking for. And so so one has to understand. So basically, what you maybe the picture I have in mind, I don't know if it's the best picture. You basically you have a MK here. You have some fiber SK, or some projections, and you have A here, and then you have, as in Erwan's talk, well, you have different. In SK, you have some directions, which are the directions, the tangent directions, which are actually in VK. So which are exactly the tangent directions you hit if you lift the disk from A to MK. So which are the relevant tangent directions for us. And sometimes, well, it just so happens that in those tangent directions, you have something which is horizontal. And quite remarkably, the set where you actually have something which is horizontal is actually very small. And so one has to understand. the horizontal tangent vectors in dk. And so as Erwan did yesterday, so you introduce mk0, which is a set of all x in mk such that vk intersect with its t mk over sk at x is different from 0, and you let sk0 to be 2k mk0, including in sk. So what Erwan explained yesterday is that at least when S is just a point, then this guy here is just the projectivization of V of A. And so this is almost true in any situation, is that for any sk 0 is actually equal to P of A times S. So it's isomorphic. So you have a way of lifting tangent vectors, which was explained by yesterday, to any order of jets. And this is actually all you get. Also horizontal things you get are actually like this. And you also have mk of 0 is equal to A times P of A times S. So you have some subvariety here, which is very small with respect to this. And all those tangent vectors, which are for us the bad vectors, which are the ones we want to avoid, are actually located above this subset. Okay, and now I really come to what starts to be a bit rough, is that what you actually, now we will actually work. So of course, when S is a point, so you work with some subvariety of A, right? And so here what we will do, we will work with some subvariety of A times S. And we will even start with just a closed subscheme. I think it's maybe, now I cannot, don't remember exactly at which point it's relevant, but anyways. So you take, the setting is the following. You take X included in A times S, a closed subscheme. And then you can lift it when K to XK included in, which I call M, MK, which is equal to A times SK, right? So you have some, so of course, if it's smooth, this is just the May simply jet tower. If you have some singularities, you can actually get something else above here, which actually even might be empty if X is of dimension 0, or you get something somehow complicated. But anyways, and so you will consider, of course, PK, XK, SK. So in Erwan's talk, this was not exactly the same thing, right? In Erwan's talk, this was a Zariski closure of the lift of an entire curve. And so here, this is not the same thing. And now you fix L as a variable on A. And quite remarkably, you have to introduce the Hilbert polynomials of the fibers of this map here. For any S in SK, let PXKS be the Hilbert polynomial of XKS with respect. So XK is a fiber of and so of XKS with respect to L, it's just H0 of XKS LSM, right? So here, or L, yeah, L, yeah, you can write it like this. So here, of course, XKS is a subvariety of A because you are in a product, right? So each fiber is a subvariety of A. So you can look at its Hilbert polynomial, and you set P max to be the maximum with respect to the natural order on polynomials in xk of P xks. So it's the biggest Hilbert polynomial you can get, and then you consider actually the locus where tk, which will just be the locus of all z in sk, such that the Hilbert polynomial at S is the maximum value. So this is if x ks is different from if xk is different non-empty. And as I said, xk could be empty. So this actually these degenerate cases are somehow important for the inductions, and empty if xk is empty, which can be the case if x is zero-dimensional. Yeah, and just let me take 2 minutes to say something, because I don't want to end here. And so the lemma, the important lemma, is that there exists a mu bigger than 0, such that if T is a connected component of T mu, then there exists B in A, an abelian subvariety. So sorry, I should add here, suppose XS different from A for all S in A. So suppose you don't have any, you never have a trivial, an entire fiber here in this projection here. So it's a technical point, but anyways, so a subvariety then such that for all epsilon bigger than 0, there exists an open subset U in S mu with P included in U and rho bigger than 0, such that you have this inequality here mu for all x in A times U and for all Px in a B mu x, which is included in Tx of A times S mu. And you have so Pb, which is just a quotient from A to AB, A over B, omega A and omega A over B invariant matrix, so matrix, and omega A, omega S mu, any matrix. So maybe I will just a few comments here. So basically, it tells you that okay, if ever we didn't have any abelian subvariety, right? then this B here, which exists, would be necessarily trivial. And so here you would just have the metric with respect to omega A, which is the same thing as here. So I didn't say this vector. So you have a part which is on A and the part which is on the second factor. And so I just split it into A part and the second factor part. So these are just a natural number, the numbers you can canonically associate to this equation. And so suppose that B is trivial, then you can, this epsilon, you can put it here as well. And then you would just have that this number here would be smaller than some constant than this number here. And by integrating this relation, basically, you would get that the characteristic function with respect to A would be smaller than the characteristic function with respect to so jet space, which would be smaller itself and the characteristic function with respect to A, thanks to the tautological inequality. So right, so if you have B, if you don't have any abelian subvariety, somehow this you would be able to recover the proof once again that Erwan told you. But since you have an abelian subvariety, if you see that you have a problem, if ever this vector here is a horizontal vector, because if it's a horizontal vector and you don't have the quotient here, which would be what you want, you don't actually want the quotient, you just want the metric with respect to A, then this would be, if the vector is horizontal non-trivial, this would be something which is strictly bigger than 0. But this value here, because it's horizontal, this is 0. So this would be equal to 0, right? And so this inequality would not be able to have this inequality for some horizontal vectors here without any B here. And so this somehow takes into account this non-horizontality thing. And so just, this might be very weird the first time you see this, that you actually have to look at some thing which depends on the Hilbert polynomials. And so why is this relevant? So I will explain this tomorrow. Is basically that if your Hilbert polynomial is constant, then you have a flat family. And it just so happens that if you have in a product of an abelian variety with something else, a flat family of abelian subvarieties of abelian varieties, then it so happens that the stabilizer of each fiber of this family is actually the same, is invariant. And this is where the flatness actually will come into play. That for any such family here, you can, every such component, you extract some flat family. And with the same argument as Erwan did yesterday, for each fiber of this flat family, you get some abelian variety. And actually, you will be able to relate all those abelian subvarieties thanks to the flatness. And this is where somehow it's crucial to use this. I stop here. If there are no questions, we can start again at 11. As usual.